The universe is expanding, and it's doing so faster than ever before. What if the very fabric of our universe is being stretched by an unseen force, pushing galaxies apart at an accelerating rate? For decades, scientists have been listening for the faint echoes of this mysterious phenomenon, known as dark energy. Join us as we explore the cutting-edge methods used to detect its subtle presence and uncover what it means for the ultimate fate of our cosmos. Our story begins in the early 20th century, a time of great curiosity and transformation. The world was changing rapidly, with new technologies and ideas reshaping how people saw themselves and their place in the cosmos. In the quiet halls of observatories, under the vast star-studded sky, astronomers were embarking on a journey that would forever alter humanity's understanding of the universe. At this time, the prevailing belief among scientists was that the universe was eternal and unchanging, a static, infinite expanse where stars and galaxies had always existed, fixed in their positions. This view had persisted for centuries, rooted in both philosophical tradition and the apparent stability of the night sky. Yet beneath this calm surface, a revolution was brewing, one that would challenge the very foundations of cosmology. Astronomers, armed with increasingly powerful telescopes, began to peer deeper into the cosmos, uncovering a universe far grander and more enigmatic than previously imagined. These telescopes, marvels of engineering, allowed scientists to collect faint light from distant stars and galaxies, revealing details that had been hidden from view for millennia. Night after night, astronomers meticulously recorded their observations, charting the positions and movements of celestial objects with unprecedented precision. As they gazed further into the depths of space, they discovered that the universe was not a static backdrop, but a dynamic, ever-changing tapestry. New galaxies appeared where none had been seen before, and strange patterns in the light from distant nebulae hinted at mysteries yet to be unraveled. The universe, it seemed, was alive with motion and transformation. Among these pioneers was Edwin Hubble, a man whose curiosity and determination would lead to one of the most profound discoveries in the history of science. Hubble, working at the Mount Wilson Observatory in California, used the world's most powerful telescope to study distant galaxies. His observations were meticulous, his methods rigorous, and his insights revolutionary. Hubble was not content to simply catalog the positions of galaxies. He wanted to understand their nature, their distances, and their motions. Through painstaking analysis, he began to notice a remarkable pattern, one that would forever change our perception of the cosmos. Hubble's meticulous measurements of distant galaxies revealed a startling truth. The universe was not static and unchanging, as previously believed, but rather it was expanding, with galaxies hurtling away from each other at incredible speeds. By analyzing the light from these galaxies, Hubble observed a phenomenon known as redshift. The wavelengths of light were stretched, shifted toward the red end of the spectrum, indicating that the galaxies were moving away from us. The farther away a galaxy was, the faster it appeared to be receding. This relationship, now known as Hubble's law, provided the first direct evidence that the universe itself was growing larger with time. The implications were staggering. If the universe was expanding, then it must have been smaller in the past, perhaps even originating from a single primordial point. This discovery, a cornerstone of modern cosmology, shattered the long-held view of a static universe and ushered in a new era of understanding. The idea that the cosmos was in motion, evolving, and changing over time challenged centuries of scientific and philosophical thought. It forced astronomers, physicists, and philosophers alike to reconsider their assumptions about the nature of reality. The universe was no longer a tranquil, unchanging expanse, but a dynamic, evolving entity with a history and perhaps a destiny. The realization that everything we see, the stars, the galaxies, even the very fabric of space itself, was once compressed into a single, unimaginably dense point, was both awe-inspiring and humbling. The expanding universe implied a beginning, a point in time when the cosmos was infinitely dense and hot, an event we now call the Big Bang. This concept, radical and controversial at first, suggested that the universe had a finite age and a dramatic origin. In the earliest moments after the Big Bang, the universe was a seething cauldron of energy and particles, expanding and cooling as it evolved. Over billions of years, matter coalesced to form stars, galaxies, and eventually the complex structures we observe today. The Big Bang Theory provided a powerful framework for understanding the evolution of the cosmos, explaining not only the expansion of space, but also the abundance of elements, the formation of galaxies, and the cosmic microwave background radiation, the faint afterglow of the universe's fiery birth. Hubble's observations, coupled with Einstein's theory of general relativity, provided the foundation for the Big Bang model, a framework that elegantly explains the evolution of the universe from its earliest moments to the present day. Einstein's equations described how matter and energy shape the geometry of space and time, predicting that the universe could expand, contract, or remain static depending on its contents and the forces at play. When combined with Hubble's empirical data, these theoretical insights painted a coherent picture of a universe that began in a hot, dense state and has been expanding ever since. This synthesis of observation and theory marked a triumph of human curiosity and ingenuity, demonstrating the power of science to unravel the deepest mysteries of existence. However, the expanding universe presented a conundrum, a cosmic puzzle that would baffle even the brilliant mind of Albert Einstein. If the universe was expanding, what was driving this expansion? Would it continue forever, or would gravity eventually halt and reverse it, leading to a cosmic collapse? These questions sparked intense debate among scientists, fueling new lines of inquiry and inspiring generations of researchers to probe the fundamental nature of the cosmos. The universe, it seemed, was not only more dynamic than previously thought, but also more mysterious, filled with forces and phenomena that defied easy explanation. Einstein's theory of general relativity, while successfully explaining the behavior of gravity on large scales, seemed to imply that the expansion of the universe should be slowing down over time. According to the equations, the mutual gravitational attraction of all the matter in the universe should act as a brake, gradually decelerating the expansion initiated by the Big Bang. If the universe contained enough matter, this deceleration could eventually bring the expansion to a halt, or even reverse it, leading to a big crunch. If not, the universe would continue to expand forever, but at an ever-decreasing rate. The fate of the cosmos, it appeared, hinged on a delicate balance between the outward push of expansion and the inward pull of gravity. Gravity, the force that attracts objects with mass, should act as a cosmic brake, gradually slowing down the expansion initiated by the Big Bang. Every star, every galaxy, every particle of matter in the universe exerts a gravitational pull on every other, weaving an intricate web of attraction that binds the cosmos together. Over vast stretches of time and space, this force shapes the evolution of galaxies, the formation of stars, and the ultimate destiny of the universe itself. Yet, as astronomers measured the rate of expansion, they found that the universe was not behaving as expected. The expansion was not slowing as much as predicted, hinting at the presence of unknown forces or substances influencing the cosmic balance. To reconcile his theory with the prevailing notion of a static universe, Einstein introduced a fudge factor, a term he called the cosmological constant, denoted by the Greek letter lambda. This mathematical addition to his equations represented a repulsive force, an energy inherent to space itself that could counteract the attractive pull of gravity. By carefully tuning the value of the cosmological constant, Einstein was able to construct a model of the universe that remained perfectly balanced, neither expanding nor contracting. For a time, this solution seemed elegant, preserving the cherished idea of a static cosmos while remaining consistent with the laws of physics. This cosmological constant represented a repulsive force, a sort of anti-gravity that counteracted the attractive pull of gravity, thus maintaining a static universe. In Einstein's model, this mysterious energy permeated all of space, exerting a gentle push that exactly balanced the inward tug of matter. The concept was bold, even audacious, suggesting that the fabric of space itself possessed properties beyond those of ordinary matter and energy. Yet, the introduction of the cosmological constant was not without controversy. Many physicists viewed it as an ad hoc fix, a mathematical trick designed to preserve a cherished but ultimately flawed worldview. Little did Einstein know that his biggest blunder, as he would later call it, would eventually play a central role in our understanding of the universe's most perplexing mystery. Decades after Einstein abandoned the cosmological constant, new observations would reveal that the universe's expansion is not slowing down, but accelerating, a discovery that would resurrect lambda and transform it from a mathematical curiosity into a profound clue about the nature of reality. Today, the cosmological constant stands at the heart of one of the greatest scientific mysteries of our time. The search to understand dark energy, the enigmatic force driving the accelerated expansion of the cosmos. As we continue to explore the universe, we are reminded that every answer brings new questions, and that the story of the cosmos is far from complete. As the 20th century drew to a close, the field of astronomy was undergoing a quiet revolution. The telescopes that once peered dimly into the night sky had evolved into powerful, precision instruments, capable of capturing the faintest glimmers of light from the farthest reaches of the cosmos. With each technological leap, astronomers found themselves able to probe deeper into the universe's past, unraveling mysteries that had eluded humanity for centuries. One of the most pressing questions was deceptively simple. How fast is the universe expanding, and is that expansion changing over time? For decades, scientists had assumed that gravity, the force that binds stars, planets, and galaxies together, would act as a cosmic brake, gradually slowing the universe's expansion. The prevailing wisdom was that, given enough time, gravity might even halt the expansion altogether, perhaps causing the universe to contract in a dramatic reversal known as the Big Crunch. But to test these ideas, astronomers needed more than just theories. They needed precise measurements, and for that, they required new tools and new methods. The quest to measure the cosmic expansion led astronomers to seek out cosmic beacons, objects so bright and so consistent in their properties that they could serve as reliable yardsticks across the vastness of space. Among the most valuable of these were Type 1a supernovae. These spectacular explosions occur when a white dwarf star, the dense remnant of a once sun-like star, accumulates matter from a companion until it reaches a critical mass and ignites in a thermonuclear blaze. The result is an explosion of such intensity that for a brief moment, a single star can outshine an entire galaxy. But what made Type 1a supernovae truly invaluable was their remarkable uniformity. No matter where they occurred in the universe, these explosions reached nearly the same peak brightness, making them what astronomers call standard candles. By comparing the observed brightness of a supernova to its known intrinsic brightness, scientists could calculate its distance with impressive accuracy. The story of Type 1a supernovae is a tale of cosmic recycling and cataclysm. When a white dwarf siphons material from a neighboring star, it slowly grows heavier, inching closer to a critical threshold. Once it crosses this limit, the star can no longer support its own weight, and a runaway fusion reaction tears it apart in a matter of seconds. The explosion is so powerful that it disperses elements like carbon and oxygen into space, seeding future generations of stars and planets. But for astronomers, the true value of these explosions lies in their consistency. Like cosmic lighthouses, they shine with a predictable brilliance, allowing scientists to map the universe's structure and measure its expansion with unprecedented precision. By studying the light from these distant supernovae, astronomers could peer billions of years into the past, observing the universe as it was when these explosions first occurred. Armed with these cosmic yardsticks, teams of astronomers embarked on an ambitious campaign to chart the universe's expansion history. They scoured the skies for the telltale signs of distant supernova, using the world's most advanced telescopes to capture their fleeting light. Each new discovery was a window into a different era of cosmic history, a snapshot of the universe at a particular moment in time. By measuring the distances to these supernova and comparing them to their redshifts, a measure of how much the universe has stretched since the light left the explosion, astronomers could reconstruct the universe's expansion over billions of years. The hope was that these observations would reveal whether the expansion was slowing, steady, or perhaps even speeding up. The prevailing expectation, rooted in decades of theoretical work, was that the farther away a supernova was, the brighter it would appear compared to a universe with constant expansion. If gravity was slowing the expansion, then the light from distant supernovae would have traveled through a universe that was expanding more rapidly in the past, making them appear closer, and thus brighter, than they would in a universe with unchanging expansion. Astronomers meticulously plotted the brightness and redshift of each supernova, building a detailed map of the universe's growth. The data, they believed, would confirm the slow but steady deceleration of cosmic expansion, a universe gradually yielding to the relentless pull of gravity. But as the data poured in, a startling pattern began to emerge, one that defied all expectations. In the late 1990s, two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, announced results that would send shockwaves through the scientific community. Their painstaking observations revealed that distant Type 1 supernovae were not brighter than expected. In fact, they were fainter, significantly so. This was not a minor discrepancy, but a profound contradiction of the established view. The implications were staggering. Rather than slowing down, the expansion of the universe was actually speeding up. The cosmos was not coasting gently to a halt, but racing ever faster into the void. The faintness of these distant supernovae was the smoking gun. It meant that the light from these explosions had traveled farther than expected, through a universe that had expanded more rapidly than anyone had imagined. The only way to explain this observation was to accept a radical new idea. Some unknown force was overpowering gravity, driving galaxies apart at an accelerating pace. This revelation upended decades of cosmological thinking and forced scientists to confront the possibility that the universe was far stranger than they had ever suspected. The discovery of cosmic acceleration was nothing short of a scientific earthquake. It challenged the very foundations of physics and cosmology, raising questions that no one had thought to ask. How could the universe be accelerating when gravity should be slowing it down? What was the nature of the mysterious force responsible for this acceleration? The news reverberated through the halls of academia, sparking debates, conferences, and a flurry of new research. For many scientists, it was a moment of both excitement and bewilderment, a reminder that the universe still held secrets capable of overturning even the most cherished theories. To account for this unexpected acceleration, cosmologists proposed the existence of a new unseen component of the universe, an enigmatic force that acted in opposition to gravity. This force, which would come to be known as dark energy, was unlike anything previously imagined. It did not clump or cluster like ordinary matter, nor did it emit or absorb light. Instead, it seemed to permeate all of space, exerting a repulsive pressure that pushed galaxies apart with ever-increasing speed. The concept of dark energy was both revolutionary and unsettling, hinting at a universe governed by laws that were only beginning to be understood. Dark energy quickly became one of the most profound mysteries in all of science. Its effects were unmistakable, yet its nature remained elusive. Was it a property of space itself, as Einstein had once speculated with his cosmological constant, or was it the manifestation of some new exotic field or particle, as yet undiscovered? The search for answers drove physicists and astronomers to develop new theories, design new experiments, and launch new missions to probe the universe's deepest secrets. The stakes were nothing less than a complete revision of our understanding of the cosmos. As the evidence mounted, it became clear that dark energy was not a minor player in the cosmic drama. In fact, it appeared to dominate the universe's energy budget, accounting for nearly 70% of all the energy in existence. Ordinary matter, the stuff of stars, planets, and people, made up less than 5%, while dark matter, another mysterious component, contributed about 25%. This realization was nothing short of revolutionary. The universe, it seemed, was not only expanding, but doing so under the influence of a force that dwarfed all others. The discovery of dark energy forced scientists to rethink everything they thought they knew about the cosmos, from its origins to its ultimate fate. The impact of this discovery rippled through every corner of cosmology. The old models, which pictured a universe dominated by matter and governed by the steady hand of gravity, were suddenly obsolete. In their place arose a new paradigm, one in which dark energy played the starring role. The laws that had once seemed immutable were now open to revision, and the very fabric of reality appeared more malleable than ever before. Cosmologists found themselves grappling with questions that reached to the heart of existence. What is the true nature of dark energy? How does it shape the evolution of the universe? And what does it mean for our place in the cosmos? The familiar picture of a universe gradually slowing under the influence of gravity was swept away, replaced by a far more complex and mysterious reality. The cosmos, once thought to be a simple interplay of matter and energy, was now revealed as a dynamic, ever-changing tapestry shaped by forces both seen and unseen. The discovery of dark energy marked a turning point in our quest to understand the universe, a reminder that, even in an age of remarkable scientific achievement, the cosmos still holds surprises beyond our wildest imagination. As astronomers continue to probe the depths of space and time, the mystery of dark energy stands as both a challenge and an invitation. To look deeper, to question more boldly, and to embrace the unknown in our ongoing journey to comprehend the universe. The late 20th century brought with it a revelation that would forever change our understanding of the cosmos. Astronomers, peering deep into the universe with powerful telescopes, noticed something astonishing. Distant galaxies were not just moving away from us, but they were accelerating in their retreat. This unexpected observation sent shockwaves through the scientific community. The discovery of cosmic acceleration and the subsequent realization that a mysterious force, soon to be called dark energy, was driving this expansion, marked a profound turning point in cosmology. For decades, scientists had assumed that gravity, the force that binds stars and galaxies together, would gradually slow the universe's expansion. Instead, they found the opposite. The universe was speeding up, propelled by an unknown energy that seemed to defy all previous expectations. Scientists were faced with a profound mystery. What is this invisible force that makes up nearly 70% of the universe's energy budget and drives its accelerating expansion? The realization that most of the cosmos is dominated by something we cannot see, touch, or directly measure was both humbling and exhilarating. Dark energy, as it came to be known, is not just a minor player in the cosmic drama. It is the main character, shaping the fate of the universe on the grandest scales imaginable. The pie charts and infographics that now populate textbooks and research papers tell a startling story. Ordinary matter, the stuff that makes up stars, planets, and people, accounts for less than 5% of the universe. Dark matter, another invisible component, makes up about 25%. But it is dark energy, this enigmatic force, that fills the remaining 70%, dominating the cosmic landscape. The quest to understand dark energy became a paramount challenge, driving research at the forefront of physics and astronomy. Around the world, teams of scientists mobilized, building ever more sensitive instruments and launching ambitious surveys to map the universe in unprecedented detail. Observatories perched atop remote mountains, space telescopes orbiting high above the Earth, and vast collaborations of researchers all focused their efforts on unraveling the secrets of this mysterious force. The stakes could not be higher. Understanding dark energy means unlocking the ultimate fate of the universe itself. Will the cosmos expand forever, tear itself apart, or eventually slow down and collapse? The answer depends on the true nature of dark energy. The simplest explanation for dark energy, and the one that fits most neatly within the framework of general relativity, is the cosmological constant, a term first introduced by Albert Einstein over a century ago. In his quest to describe a static universe, Einstein added this fudge factor to his equations, only to later discard it when the universe was found to be expanding. Yet, in a twist of scientific fate, the cosmological constant returned to center stage as a possible explanation for the accelerating universe. This term, represented by the Greek letter lambda, acts as a kind of built-in energy to space itself, a subtle pressure that pushes the fabric of the cosmos outward. In this context, the cosmological constant represents the energy density of the vacuum of space itself, an intrinsic energy inherent to the very fabric of space-time. Even in the absence of matter and radiation, the vacuum is not truly empty. Instead, it seethes with quantum fluctuations, virtual particles popping in and out of existence, and a subtle energy that permeates all of space. This vacuum energy, though invisible and undetectable by ordinary means, exerts a real and measurable effect on the universe as a whole. It is this energy that, according to the cosmological constant hypothesis, is responsible for the observed acceleration of cosmic expansion. This vacuum energy, unlike matter and radiation, does not dilute as the universe expands. As galaxies move farther apart and the cosmos grows ever larger, the density of matter and light decreases, spreading thinner and thinner across the vastness of space. But the energy of the vacuum remains constant, providing a steady, unrelenting outward pressure that drives the accelerating expansion. This property makes dark energy fundamentally different from anything else we know in physics. It is as if the universe has a built-in engine, quietly and persistently pushing everything apart with no sign of slowing down. While the cosmological constant provides a mathematically elegant solution to the problem of dark energy, it comes with its own set of theoretical challenges. The equations are beautiful, and the fit to observational data is impressive, but the underlying physics remains deeply puzzling. Why does the vacuum have the energy it does? Why is the cosmological constant so small, yet not exactly zero? These questions have sparked intense debate and speculation among physicists, leading to a host of alternative theories and models. The most pressing of these is the so-called cosmological constant problem, which highlights the enormous discrepancy between the observed value of the cosmological constant and the value predicted by quantum field theory. According to our best understanding of quantum physics, the vacuum should be teeming with energy, so much in fact that the universe would have blown itself apart long ago. Yet, the actual measured value of the cosmological constant is staggeringly small, smaller by a factor of up to 10^120 than theoretical predictions. This is perhaps the greatest mismatch between theory and observation in all of science, a cosmic puzzle that has resisted solution for decades. This discrepancy, a difference of many orders of magnitude, suggests that our understanding of either gravity, quantum physics, or both is incomplete. It is a glaring signpost pointing toward new physics, perhaps a deeper theory that unites the quantum and the cosmic, or a radical revision of our most cherished ideas. Some researchers speculate that dark energy might not be a constant at all, but a dynamic field that evolves over time. Others propose that our universe is just one of many in a vast multiverse, each with its own laws and constants. The true nature of dark energy remains one of the most tantalizing mysteries in all of science. Despite these theoretical conundrums, the cosmological constant, often referred to as lambda, became a cornerstone of the standard model of cosmology, known as the lambda-CDM model. This model weaves together the mysterious dark energy, the invisible dark matter, and the ordinary matter we see around us into a coherent framework that describes the evolution of the universe from the Big Bang to the present day. Lambda-CDM has become the foundation upon which modern cosmology is built, guiding observations, experiments, and theoretical work across the globe. This model, which incorporates both dark energy and cold dark matter, has been remarkably successful in explaining a wide range of cosmological observations. From the faint afterglow of the Big Bang, the cosmic microwave background radiation, to the intricate web of galaxies and clusters that span the universe, Lambda-CDM provides a powerful and predictive framework. Yet, for all its successes, the true nature of dark energy remains elusive. As scientists continue to probe the cosmos with ever greater precision, the hope is that new discoveries will shed light on this mysterious force, revealing not only the fate of the universe, but also the fundamental laws that govern reality itself. The mystery of dark energy has, captivated the imaginations of scientists and the public alike, becoming one of the most profound and enduring puzzles in all of modern science. For decades, astronomers have gazed into the depths of the cosmos, searching for clues that might reveal the true nature of this invisible force. The more we learn, the more we realize how much remains hidden, just out of reach, waiting to be discovered. Dark energy is not just a scientific enigma, it's a cosmic riddle that challenges our very understanding of the universe and our place within it. This relentless curiosity has sparked a quest for answers that continues to this day, driving generations of scientists to push the boundaries of knowledge and technology. The search for dark energy is not just about solving a single problem, it's about unraveling the very fabric of reality itself. The Lambda-CDM model, which stands as the current standard model of cosmology, has been remarkably successful in explaining a wide range of observations, from the cosmic microwave background to the large-scale structure of the universe. It elegantly weaves together the roles of dark matter, dark energy, and ordinary matter, providing a framework that matches much of what we see in the cosmos. Yet, despite its successes, the Lambda-CDM model does not provide a complete picture and leaves many fundamental questions unanswered. It's as if we have assembled the edges of a cosmic puzzle, but the most intriguing pieces at the center are still missing. The model describes how dark energy behaves, but not what it actually is or why it exists. The nature of dark energy remains elusive, shrouded in mystery. Is it a property of space itself, a new kind of field, or something even stranger that we have yet to imagine? Its presence is inferred from the way it accelerates the expansion of the universe, but its true identity is still unknown. Its existence challenges our understanding of fundamental physics, forcing us to confront the possibility that our current theories may be incomplete or even fundamentally flawed. The discovery of dark energy has opened a new chapter in the story of science, one that demands fresh ideas and bold thinking. To address these fundamental questions, scientists are pursuing a multifaceted approach, drawing on the expertise of astronomers, physicists, engineers, and mathematicians from around the world. This global collaboration is essential, as the quest to understand dark energy requires both theoretical innovation and technological advancement. Researchers are combining theoretical exploration with increasingly precise observations of the universe, using every tool at their disposal to probe the cosmos for answers. The interplay between theory and observation is at the heart of this scientific adventure, with each new discovery raising fresh questions and inspiring new lines of inquiry. On the theoretical front, physicists are exploring a plethora of alternative explanations for dark energy, each with its own set of predictions and challenges. Some theories suggest that dark energy is a manifestation of the vacuum energy predicted by quantum mechanics, while others propose that it arises from the dynamics of new, undiscovered fields permeating space. Other researchers are investigating the possibility that our understanding of gravity itself may need to be revised, ranging from modifications to Einstein's theory of general relativity to entirely new frameworks that could explain the accelerating universe without invoking dark energy at all. Still others are searching for evidence of new, exotic particles and fields that could interact with the cosmos in subtle ways, leaving behind signatures that might one day be detected by our instruments. These ideas, while speculative, are grounded in the rigorous mathematics and logic that underpin modern physics. These alternative theories offer intriguing possibilities, expanding our imagination and challenging us to think beyond the limits of current knowledge. They invite us to consider a universe far stranger and more complex than we ever imagined. If proven correct, some of these ideas could potentially resolve some of the theoretical challenges associated with the cosmological constant, such as the so-called fine-tuning problem, which asks why the energy density of dark energy is so small compared to what quantum theory predicts. On the observational front, astronomers are harnessing the power of cutting-edge telescopes and instruments, pushing the limits of what we can see and measure. These technological marvels are designed to capture the faintest signals from the farthest reaches of the universe, allowing us to study the properties of dark energy with unprecedented precision. Teams of scientists work tirelessly to design, build, and operate these observatories, often in remote locations where the skies are darkest and clearest. Their efforts are driven by the hope that, with each new observation, we will come one step closer to unraveling the secrets of dark energy. Large-scale surveys of galaxies, such as the Dark Energy Survey, are mapping the cosmos in exquisite detail, cataloging the positions and movements of millions of galaxies across vast stretches of space and time. These surveys provide a treasure trove of data, revealing subtle patterns that may hold the key to understanding dark energy. The upcoming Large Synoptic Survey Telescope, now known as the Vera C. Rubin Observatory, promises to revolutionize our view of the universe by capturing a dynamic, ever-changing portrait of the night sky. Its powerful cameras will scan the heavens night after night, building a vast archive of cosmic events and phenomena. These ambitious projects aim to map the distribution of matter in the universe, tracing the intricate web of galaxies and dark matter that stretches across the cosmos. By studying how this cosmic web evolves over time, scientists hope to uncover the fingerprints of dark energy and its influence on the growth of structure in the universe. Observing the evolution of galaxies and clusters over billions of years provides crucial clues about the nature of dark energy and its role in shaping the universe. These observations help us test competing theories and refine our models, bringing us ever closer to the truth. These surveys, combined with observations of distant supernova, exploding stars that serve as cosmic mileposts, allow astronomers to measure the expansion rate of the universe with remarkable accuracy. By comparing the brightness and distances of these supernova, scientists can track how the universe's expansion has changed over time. Another powerful tool is the study of the cosmic microwave background radiation, the faint afterglow of the Big Bang. This ancient light carries a wealth of information about the early universe and provides a critical test for theories of dark energy. By comparing the predictions of different dark energy models with the latest observational data, cosmologists can rule out certain possibilities and focus on the most promising explanations. This process of testing and refinement is at the core of the scientific method, driving progress and deepening our understanding. With each new discovery, we peel back another layer of the cosmic onion, revealing new mysteries and deeper questions. The enigmatic force we call dark energy continues to defy easy explanation, but it also inspires awe and wonder, reminding us of the vastness and complexity of the universe we inhabit. The quest to understand dark energy is pushing the boundaries of observational astronomy, driving the development of ever more sophisticated instruments and techniques. These advances not only help us study dark energy, but also open new windows onto the universe, enabling discoveries we have yet to imagine. As we look to the future, the search for answers continues. The journey to understand dark energy is far from over, but with each step, we come closer to unlocking the secrets of the cosmos. In this grand adventure, every question leads to new discoveries, and every discovery brings us closer to understanding the universe and ourselves. The story of dark energy is a tale that stretches across centuries, woven from the threads of scientific discovery, profound mystery, and the enduring human quest to comprehend the universe we inhabit. It is a narrative that begins with our earliest ancestors gazing up at the night sky, wondering about the lights that dotted the darkness, and extends to the most advanced observatories and telescopes of our modern era. From the first myths and legends about the heavens to the precise measurements of cosmic expansion, humanity has always been driven by a desire to understand what lies beyond our world. This journey highlights both the remarkable progress we have made in unraveling the secrets of the cosmos and the vast unknowns that still lie ahead. Each discovery has opened new doors, revealing deeper layers of complexity and wonder, while also reminding us of how much remains hidden in the darkness. The discovery of cosmic acceleration at the end of the 20th century and the emergence of dark energy as a dominant force in the universe have revolutionized our understanding of the cosmos. These findings have challenged us to rethink the fundamental laws of physics, forcing scientists to confront questions that once seemed unimaginable. What is driving the universe to expand faster and faster? What is the true nature of this mysterious energy that makes up nearly 70% of everything that exists? This documentary invites you to embark on a captivating journey into the heart of this cosmic enigma. We will travel from the earliest observations of the stars to the latest discoveries at the frontiers of science, following the trail of evidence that has led us to the concept of dark energy. We will delve into the history of cosmological discoveries, exploring how ancient civilizations mapped the heavens and how the invention of the telescope transformed our view of the universe. From Galileo's first glimpses of distant planets to Edwin Hubble's revelation that the universe is expanding, each breakthrough has brought us closer to understanding the cosmos. We will explore the current state of our understanding of dark energy, examining the evidence that points to its existence and the theories that attempt to explain its mysterious properties. Scientists have proposed everything from a cosmological constant to exotic new fields and particles, but the true nature of dark energy remains one of the greatest puzzles in modern science. We will also examine the cutting-edge research that is pushing the boundaries of knowledge. Around the world, teams of astronomers, physicists, and engineers are building ever more powerful instruments to probe the depths of space, searching for clues that might unlock the secrets of dark energy. Along the way, we will encounter fascinating concepts, from the explosive deaths of stars that serve as cosmic mileposts to the subtle distortions of light caused by the invisible scaffolding of the universe. Each observation, each experiment, brings us a step closer to understanding the forces that shape our reality. We will also confront profound questions that continue to captivate the imaginations of scientists and the public alike. What is the ultimate fate of the universe? Will it expand forever, or will some unknown force bring it to an end? How does dark energy fit into the grand tapestry of cosmic evolution? The quest to understand dark energy is a journey into the unknown, a voyage that takes us to the very edge of human knowledge. It is a challenge that demands creativity, perseverance, and a willingness to question everything we think we know. This journey is also a testament to the boundless curiosity and ingenuity of the human spirit. Throughout history, we have looked beyond the horizon, seeking answers to questions that once seemed impossible to solve. The story of dark energy is the latest chapter in this epic adventure. It is a journey that transcends the boundaries of scientific disciplines, bringing together ideas from physics, astronomy, mathematics, and philosophy. The search for dark energy unites researchers from every corner of the globe in a shared pursuit of knowledge, reminding us that the quest to understand the universe is a truly universal endeavor. Physicists, astronomers, and cosmologists work side by side, sharing insights and discoveries, driven by a common goal. Their efforts are supported by engineers, computer scientists, and countless others who contribute their expertise to this grand project. As we venture deeper into this cosmic mystery, we can be certain that the universe will continue to surprise us. Each new observation has the potential to overturn our assumptions, revealing new wonders and challenges along the way. The process of discovery is never-ending, and the more we learn, the more questions arise. The universe is a vast and dynamic place, filled with phenomena that defy easy explanation. Our exploration of dark energy is not just a scientific endeavor, but a testament to our innate desire to understand our place in the grand scheme of the cosmos. It is a journey that connects us to every generation that has ever looked up at the night sky and wondered what lies beyond. This journey reminds us of the vastness of the universe and the countless mysteries it holds. It is a humbling experience, one that inspires awe and curiosity in equal measure. As we continue to explore the cosmos and unravel its secrets, we inspire future generations to dream, to question, and to reach for the stars. The story of dark energy is far from over. It is a journey that will continue for as long as there are those who dare to ask, what lies beyond? And so we invite you to join us as we set out on this extraordinary adventure, a journey into the unknown, where every answer leads to new questions, and the universe itself becomes our greatest teacher.